There we go.
Okay, Michael, take it away.
Yes, okay, thank you very much.
On the air.
In the air.
Okay, well, so I'm going to use my pen to get this going. So this is heavily joint work with Chris Scott, who is indeed going to give the part of the talk, and Rachel Melrose. Okay, so what I'm going to do is talk about monopole moduli spaces and define the metric from a mathematician's point of view. And if I have time, well, between us, we will state the new results we have about the asymptotics of the metric in some regions. I also want to explain why this is a complicated problem for those of you who are not so familiar with it. I mean, the monopole moduli spaces are non-compact spaces with a very complicated structure at infinity, at least by comparison with the ALG and ALH space that we heard about from Hayo on Monday. Okay, so I thought I mean, there are lots of different places to start, and I thought I'd start, as others have, with the case of Dirac monopoles. And I'll try to give some intuition insofar as I have it for what's going on as well. Okay, so, or maybe, I mean, of course, a monopole is intrinsically a singular thing, and I noticed that Nick was very careful to talk about clusters whenever you have more than one. So maybe we should do Dirac monopole clusters. You also hear people say multi-monopole, which is almost an oxymoron, I suppose. Okay, so my setting is going to be R3, and we're going to write down a singular solution of the U1 Bogomolny equations. So I'm going to just choose a bunch of points, Z1 up to Zn, Zn in R3, so these should be distinct points. And then I'm also going to choose a bunch of positive integers, and I can write down the harmonic function phi. So we're going to choose a positive constant n, which is going to be the mass. I'm just write down the sum of these Green's functions, centered the point Z check. Okay, so this is a so Z is generically underline Z. I may forget the underlines in the future, but underline Z is the coordinate in R3. Okay, so this is a harmonic function. And as such, if so the class is D star D, so if I form star d phi, this is of course I'm fixing Euclidean metric, I should say as well. So this is a closed two form. And it has it has integral periods because of the k's and the half, in the sense that the integral star d phi, phi of 2 pi times the integral star d phi is an integer for all for any 2 star point in our function R3. So we have R3. Now we've got here's R3, and then we've got a bunch of points that we've deleted. And around each of these points, there's a small sphere Sj. If you integrate star d phi around it, you get precisely kj. You normalize it. Okay, so this integrality is important because it means that there's a bundle, a complex line bundle over this function space, plus a U1 connection. So I'm just going to call A. I mean, everything you could decorate with the configuration data of the points, but the connection A, such that the curvature of A are given 2. Okay. You need the integrality for this to be genuine line model. You don't have the integrality. You can't do this. Okay, so so the pair A phi is a direct monopole, phosphorus maybe, corresponding to our given configuration. In that it's a solution of, because I constructed this way, it's a solution of the abelian Bogomolny equations curvature is star phi. Okay. So that's the Dirac monopole. What else did I want to say about this? Well, I mean, so I think Nick would probably write this as star F is the phi, and then he'd call star F, which is a one-form B. I mean, that's the magnetic field. Right.
I think that follows from the previous line.
Of course it does, but I mean, I have to say, in your talk, you identified this with a vector B, right?
Well, I can do that R3.
Yeah, sure. Yeah, I mean,
yeah, it's important.
I mean, what I'm saying is trivial, but I mean,
No, but some of these remarks show the importance that it's Euclidean R3, and not just one's got to be more careful otherwise. Yeah.
Well, I mean, star squared is always 1 in 3 dimensions, but I mean,
all right.
okay, but, okay. So this is the I mean, insofar as I understand the physics, this is the magnetic field. Sorry, genuine. It's genuine. Okay, good. Right. Of course, I mean, locally, one can all. I mean, locally, if you trivialize line bundle locally, then you could identify A with a vector, an ordinary Euclidean vector in R3, and then this equation is also just curl A as described in classical sort of electrodynamics language. Okay, so this is the equation that we're generalizing. Okay, so we haven't. Some remarks. So, well, one remark is that if you integrate, you can compute the total charge, if you like, the case of charge. So you can compute the total charge at infinity by integrating this guy over a very large 2-sphere, and just obviously this is going to be the sum of the k's. So that each k contributes, each singularity contributes some amount of charge, and if you integrate over the sphere of infinity, you get the total charge. I also wanted to, that's one. So this is also, of course, the degree of the line bundle L over the sphere of infinity. Just doing classical things here. Right, so we haven't, I think, really had a gauge theoretic moduli space yet so far in this program. So here is a nice simple one. So you have the gauge freedom in this case. So there's a choice when I solve the equation FA is star phi is completely fixed, of course. But, I wrote it down, but there's a choice in A, because if you change A by gauge, then that equation will not change. So in this case, it's just the automorphisms of the line model L, which is just essentially smooth maps from R punctured R3 into U1, trying to preserve the fact that it's a U1 connection. So if I have a gamma, have such a gamma in here, then gamma is going to act on my solution by conjugation. So, which if you write it out explicitly is, in this case, I write it so that it generalizes in the obvious way. Conjugating, I mean, U1 is a Boolean, of course, so the action on phi is actually trivial, but it does move the connection one formed by this exact thing. Okay, so the moduli space of these guys should be the set of all pairs solving an equation modulo this gauge action. So this is with M, the Zj, and the Kj all fixed. Should be the, I just write it in words, so it's the all solutions requires given modulo this gauge group. Okay, so there's already a subtlety here, which is that this space actually has dimension -1. So that's because of the following thing. In some sense, it has dimension -1. So the point is that so it's quite easy to see that you have two solutions of the equation that's disappearing here. The statement that it's to understand this moduli space, you want to understand when two solutions of equations are actually gauge equivalent. But in fact, if you have any two such things, they are gauge equivalent in this situation. Okay, so any two solutions are gauge equivalent. But in this situation also you have the rigid circle action on the line model. You can just take gamma to be constant, and obviously that's not going to change the this equation. So if you've solved it for one gamma and you multiply gamma by a constant phase, then you will still have solved the equation. So that's the sense. So I mean, dividing out by the gauge transformation, this shows that any two are equivalent, so that means the moduli space is a point. But then you've still got this leftover circle, which means the moduli space is dimension -1. Okay, so we don't like negative dimensions. So yeah, so I always say gamma, but still have constant gauge transformations. As a residual symmetry. So we don't like that. So the thing that's usually done is just to restrict the gauge group to assume that it's the identity, assume that our gauge transformations are the identity of infinity. So this sort of replace alt L by saying alt sub 0 of L. Okay, this is enough to fix the phase. Okay. Are there any questions so far? If you think about this, this is now, you have to, well, okay, so of course, if you fix the gauge transformations to the identity as infinity, then you're not moving the connection. When I say it's infinity, I mean, well, asymptotically. In the limit, as distances go to infinity. But if you think then about what data you're actually acting on, it becomes a little bit confusing again, because if gamma tends to 1 to infinity, then you're probably not really moving the boundary value, whatever that means, of the connection. So this leads to the following. So if you think what you're actually acting on here, so this motivates the idea of framing. So this is the framed gauge group, but what's it act on? So this is the following idea that so you fix A infinity, say, connection on L near infinity, such that the curvature of A infinity minus starting phi is order 1 over mod z squared. Right, mod z squared, mod z cubed. So this means really fixing the asymptotic value of A infinity, and yeah, this really means fixing the asymptotic value of A infinity. Okay, so in some sense, the frame moduli space is the space of connections A, where you sorry, is that wrong? Yeah, so what I want to say, I think, is that so then the frame moduli space. So we make this choice of A infinity. So I should have adopted Pierre's philosophy right at the start. So frame moduli space, you consider connections A on L such that mod A minus A infinity, which is a well-defined one form, is order 1 of mod. Okay.
Why is it called framing?
Because you are fixing the, I mean, in some sense, you're not allowing the gauge transformations to act on the bundle over the sphere of infinity.
And what's the phi in that?
Oh, well, yeah, well, to maybe to bring this into focus. I mean, the point is that for any, well, what is phi? Well, phi is, of course, asymptotically, phi is IM minus this. If you expand it for large Z.
Any phi. Any
Sorry?
phi in the modular space.
Yes, well, I mean, well, I've sort of fixed the configuration, but the point is now that you can vary the points a bit, and if you don't change the charges, the two main terms in the phi are always the same, independent of the configuration. So it makes sense somehow to think of phi as being fixed up to this order, and the connection to be fixed in this sense, and then, you know, everything else is lower order terms. So, I mean, this is
What's to stop just taking A infinity to be a solution of your equation?
you can do that.
Ah, but then if I move the points, it'll still satisfy this condition.
Yeah.
For different
Yes,
functions.
yeah,
That's what you're
yeah,
just saying.
yeah, yeah,
Okay.
yeah. Yeah, so you can take A, you just
the minute
pick.
you're about to move
Yeah,
the points.
yeah, yeah. I could, but maybe I should press on. Anyway, this is the reason for going through this was supposed to be twofold. One is that when you go to non-abelian gauge groups, like SU2, for example, if you have widely separated monopole clusters, then the geometry infinity is supposed to be exactly like the geometry. And the geometry sort of somehow far from where the monopoles are is supposed to be exactly reflected by a suitable Dirac monopole. That's one thing, so it's good to understand what Dirac monopoles are. And the other thing was to try to give you some idea of this framing, which is kind of an annoyance, but an important annoyance actually, because I mean, in a minute we're going to want to define an L2 metric. I mean, you can't define L2 metric in this situation because the fields blow up. But I mean, you have the same problem at infinity for non-abelian monopoles as you do here. So, I mean, the tangent space of this frame moduli space consists of things that are order 1 over mod z squared at infinity, and those are then square integrals. So you need to fix this stuff up if you want a metric on the sort of on the space of data that you are interested in. Okay. All right. Okay, so that was one thing. But as you said, I mean, I could now go ahead and move the points, and phi will only change at lower order, and A will only change at lower order, particularly if I fix it to the highest order. And so there is then a bijection between the space of configurations of distinct points with these weights kj and this moduli space of monopoles. Of course, I mean, it's not that interesting. The bundle moves as well because it's on the tangent space. But. Okay. So anyway, I wanted to get the idea of what the Dirac monopoles are because they reflect the asymptotic behavior of monopoles and also the framing idea. Okay, one more thing I wanted to say about this is about centering. Okay, so so it's probably a bit fictitious in the case of Dirac monopole. So I just wrote one of the mod Z here, which implies I've chosen origin in R3 in order to have a distance from somewhere. If you look one further order down in the expansion of phi, you'll see a harmonic function, and it has to be of the form. This is just a positive number, so I can take it out. It has to be the form c dot z over mod z cubed, and then plus order mod z cubed. Harmonic, so you have to have this expansion. So I claim that this vector c is a natural candidate for the central mass of this configuration relative to the origin that you picked. So this vector c is the center of these things. And this is natural because if you were to shift the origin, if you figure out what happens when you change z by z, change z to z plus z naught, and c translates in the right way. So that's a definition of center of mass in this.
I'm afraid to find two moduli spaces now. The first one was with phi as given, and the second one was with fixed framing and anything.
Yeah.
So the first moduli space is point, and the second moduli space is actually 3k dimensions.
The idea is that for fixed configuration of points, the moduli space of a framed Dirac monopole is just one point. So really the moduli, if you're allowed to now move the points around, is just the configurations of points with the weights.
That was the first definition. And then the second definition is fixed framing of infinity and nothing else. Am I right?
If I fix the
It's in the shadow already.
if I fix the framing at infinity, no, if I just divide out by orc 0L, then the moduli space is the space of configurations, the space of connections over the boundary. Because I haven't divided that because the gauge groups are acting trivial on that. So that's an infinite dimensional space actually. So this is why you need to, if you're going to reduce the gauge group, you also have to reduce the freedom in the connections, otherwise you get. So for each choice of A infinity, I get a moduli space that is a point. And any t, it's like choosing a base point when you're defining the fundamental group. You choose a connection.
The framing part I understand. You can also
Yeah.
look at the moduli space of
Yeah.
solutions such that they are framed at infinity and nothing else.
Yes, yes.
And then you would get configuration space of these k points together with phases.
You would, but it's a little ill-defined because the bundle moves with the points because of the singularities.
When you fix it.
Well, if I move the points are only defined. I mean, the bundle is only defined in content of the points. So I don't. It's not like I have a fixed bundle and I'm letting other things vary.
It is, but it isn't.
It is not. Well, I mean, if I move the points, I have a different bundle. I mean,
You allow it or don't allow it? That's
You don't.
my only question. You don't.
He doesn't.
I'm not allowing. I mean, this is just for illustration, and obviously it's confused everybody totally. so it's a success.
That's right, it illustrates how easy it is to do that.
Sorry? It's yeah, okay. Sorry, I'm probably missing some deep point that's deep question.
You said the weights were positive.
The K is supposed to be positive.
Why?
Good question. I suppose in this case I don't really need it. No, in this case I don't really need it. I can have either. I mean, for monopoles. I mean, when I made the blue SU2 monopoles, I definitely. You're completely right, Gary. Like they could have had either sign in this setting. Okay. I'm leaving you with a lot to do, Evan. Right. Okay, so let me talk about SU2 monopoles. So, as in Mark's talk yesterday, we have, except I'm going to fix the rank to be 2, so we have, say, a rank 2 SU2 bundle. So I'm thinking this is a vector bundle, E over R3. And we're considering, the first approximation, pairs A phi, such that A is a connection, and associated covariant derivative operator is del A, and phi, which is the Higgs field, is a, well, this is where I should have said adjoint and so on. So this is an SU2 valued section, SUE valued section. So this is supposed to be an endomorphism of P, which is skew adjoint and trace free. Okay, so this is the space we consider, and now if E is fixed, then we consider the Bogomolny equations. I'm omitting all the variational stuff which has been covered in other talks, but the Bogomolny equations are Fa is star dA phi, so I mean we take the curvature of the connection, that's a 2 form, we take the covariant derivative for the Higgs field, that's an endomorphism value 1 form, star relates, interchanges 2 and 1 in this dimension. And so we get these equations which make sense in this dimension. Okay, we need boundary conditions. The crudest of which are that the energies should be finite, so you want these two integrals to be finite, and you want the Higgs field to be non-zero to infinity. So tends to, well, I'll make it m again rather than 1. Infinity. This is supposed to be non-zero. And in this setting, well, there are different ways to define this. So there's a total magnetic charge. Which can be defined in various equivalent ways. The cheapest is you look at phi over a large sphere of infinity, look at phi over a sphere of infinity. So this is a map from a 2-sphere into skew adjoint endomorphisms. So that's R3 less the origin. So this maps the 2-sphere to R3 minus the origin, SU2 minus the origin, which is also a 2-sphere. So this has a degree. Okay, so that's the charge. The sense in which the geometry, so I'm skipping some analysis here. The sense in which the geometry of the equations is similar asymptotically to the monopoles is the following. So if we if we at least assume that phi is sort of nicely well behaved out of infinity, which it is, then so phi is non-zero and it's skew adjoint and it's non-zero. So we can diagonalize phi raised to infinity, that's far out, in other words, and it will have, so there will be 2 eigenbundles. So phi is locally like this, infinity. And the point is that these really are eigenbundles. If you look for the subspace of E where phi acts by Im, then that will vary as you go around the sphere. And in fact, that fits together to give a bundle of degree k over the sphere of infinity. So the plus or minus Im eigenbundles are of degree plus or minus k over the 2 sphere of infinity. And in fact, the asymptotic form of the monopole is exactly what is written there, except you have to put in some diagonal things. So this is insuitable gauge, it's an asymptotic form of this is that. So in other words, identifying E with L plus, I mean, I say in a suitable gauge, it really means pull back under this isomorphism with where you've identified, you've made phi diagonal by explicitly changing to the basis of eigensections of phi, I suppose. So under this isomorphism, phi has to be diagonal by definition. What the form it takes is that's 2 by 2. Apart from that, it's exactly as before. You can show that asymptotically as a consequence the equations this tends to 0 and infinity. So the connection A is also diagonal to leading order under this isomorphism, and in fact and it has constant curvature just as the Dirac one did. So we have an asymptotic connection A infinity, and its curvature is times the over 2 times the area form. So consistently again with Cherenkov. So consistently with times the area form on S2. Okay, so this is the sense in which the asymptotically a monopole looks like a pair of Dirac monopoles because diagonally embedded. Okay, so this is what you this is the Euclidean area form on S2. And again, to get them, I'm not perhaps going to go through details, but again, to get a good moduli space, you want actually to fix your data up to this order, and you want to fix you want to make a particular choice of A infinity with this curvature, and you want to consider deviations, and you want to consider data which are within order 1 over c squared of those two chosen things. Okay, so this is phi infinity and A infinity, and you want to choose data that are close to those. I should write that down. So to define frame concepts, please. Fix A infinity with this property and phi with that property and consider pairs A5. So it's subtle and annoying, but you have to do it in order to get, again, perturbations of the data that you can actually integrate over, where you can square integrate over. So you have to do this. I mean, it's annoying you have to do it, but in some sense the choices are important. If you have any two choices, then they will be gauge equivalent. You can always move one with the other. So it really is like choosing a base point when defining a fundamental group. So any two choices are equivalent. But, okay, so then you consider, okay, so indeed the moduli space MK is the space of A phi. So given our choices, which are suppressed in the notation, which satisfy Harmonic equations modulo a base gauge group. So you have the gauge group acting, should be identity over the boundary. So this is gauge transformations. Equals 1 the boundary.
You need to specify rate of convergence for the gauge transformations.
Well, you see, what I should have done, and I regretted it in the last half hour. I mean, really, it's much better actually to assume everything. It's much better to compactify R3 as Pierre was doing, and then assume that everything is smooth off the boundary. So, in fact, these gauge transformations. So, that means that these gauge transformations in this language have asymptotic expansions in powers of 1 over mod z. But actually, you have hit upon an important point, which is I believe that to preserve these, you need the subleading term to commute with phi. So it has to be in the centralizer of phi. Otherwise, when you act, you will screw something up. You'll screw up the second order part of phi. So actually, I lied here slightly. If you want to, well, it's okay if they satisfy the Bogomolde equations. But if you look at the configuration space without solving it, then the subleading part of phi has to be a multiple of phi in this SU2 case, and otherwise it would have to commute with phi. That's probably value of phi. After that, it can be counted. Okay. Right. So that's the moduli space, and it's known to be 4K dimensional. And I should at least tell you what the metric is. It has an L2 metric, which is just induced by the L2 metric on this vast space of data before you apply the equations. So the tangent space at A phi to, I'll just write it down. So the tangent space at A phi to MK is a pair A phi. Now this is an honest one form. Both things being order of 1 over mod z squared. And being tangent to the moduli space means that they satisfy the linearized equations, which I'm just going to write as LA phi equals 0. So this is the linearized polynomial equations. And this is just a coupled version of the Hodge-Durham operator that Pierre was talking about earlier today. Fits into his framework of D plus D star. Or if you like, it's just a combination of Brandon and curve in 3 dimensions, acting in the obvious way on the bits and pieces there. So this is the linearized polynomial equations. And then you'd have to divide by infinitesimal gauge transformations. So but of course, what you actually want to do is get rid of that gauge freedom. So you take the orthogonal complements to gauge orbits, and you can do that. Actually, I've lied this. I've already incorporated that in here. So yeah, so I've identified it. So this is actually part of this equation is what Nick called Gauss's law, imposing the orthogonality of the gauge. So this is the linearized polynomial equations plus Coulomb gauge position. So this is an elliptic. This is an elliptic system of equations for data, and I should have said that we're taking the L2 null space of this system. Now there's some tricky analysis that goes in here that was first done by Taubes, and which was refined by Chris actually, to ensure that, to say that this is well defined. There's not an off-the-shelf index theorem that tells you very much about this space. It doesn't fit into the standard, some of the standard ones. Anyhow, so this is the tangent space, but because these, well, actually I said order one sets of it. So I mean, to check that this is a well-defined thing takes some work. But in any case, you can now form the L2 metric is just the following thing. You just literally integrate these guys over. Okay, I've spoken for 45 minutes and I have not got anywhere near where I wanted to get. So, do you have a break anyway? Yeah.
Go.
I think, well.
Yes.
Okay.
Part two.
Continue the talk here. So, yeah, so to motivate the theorem that I want to state, so it's important to understand, so this moduli space of monopoles is a complete hyperkähler manifold. It's very nice, but it's non-compact. So what is the sort of source of non-compactness in the moduli space? And there's a theorem, Tia and Hitchin, which I may state a little bit vaguely. But there's something to the effect that, suppose I have a sequence of monopoles in this moduli space, which has no convergent subsequence.
You really want to index your sequence by K
Oh,
as well?
yes,
That's
no,
a
I
really
really
bad
don't.
idea.
That's a really bad idea, thank you. So a sequence of monopoles with no convergent subsequence. Then in fact, there exists, well, let's say a subsequence. Just by abuse of notation, I'll just continue to call that J, and a sequence of points in R3, which is diverging. Let's see, and do I want a bunch of different sequences? Yeah, maybe.
Yeah, you want
Okay.
partition.
Sorry. So before this, let me say. So there's a subsequence, a partition of the charge. So into separate non-negative each one of those things, a sequence of points, it's called ZL, so L is 1 up to N, such that if I translate my sequence back by sort of subtracting off this sequence of divergent points, then this converges in a weak sense to a monopole, and in fact I should really say a centered monopole, whatever that means. Charge KL for each L. So sort of the picture of non-compactness in the moduli space is that we have a monopole which is sort of breaking up into lower charge monopoles that are all going off to infinity in some way. So the program is to find a compactification of this moduli space that really captures this behavior geometrically.
So I mean, the distance between disjoint pairs of sequences that go to infinity.
Yes,
Not just
sorry.
that they're going to infinity.
Right.
That's,
So
that's kind of important.
yeah, yes, that's right. So it's important that the difference between ZLJ and ZL prime J is going to infinity with J as well. Not equals L prime. So right, they're sort of going off to literally different locations at infinity. So what I'm going to talk about today is sort of the first part of this compactification, which is, so the ultimate compactification will be as a manifold with corners. What I'll describe today are the codimension 1 boundary faces, boundary hypersurfaces, which capture this behavior when so the lower charge monopoles are all going off to infinity at comparable rates. That's the picture that we're going to try to capture. Let me state sort of a slightly weak version of what we prove. In the interest of time, I think I won't be able to say much about the metric.
I'm a bit confused. What do you mean by MJ of C minus MJ?
I mean, yes. So the monopole is, you know, a configuration of fields on R3. I just mean translate back by this constant. So for each monopole MJ, this is just some constant vector I just translate back. So the idea is like, you know, these monopoles are supposed to have a location in some sense. And if I recenter them at the origin, you know, at the sequence of points that are going up to infinity, if I translate them back and center them at the origin, then everything else, I'm sort of zooming in on one monopole cluster while the other clusters are going away. And in the end, I just see this lower charge centered monopole cluster.
Still don't quite understand. So the translation's actually on R3 as well as on R3? Or...
Yes. Yeah, just everything just pulled back by translation.
Well, I think it doesn't matter up to gauge how you lift your translations.
Yeah.
I mean, we're talking about, these are in the moduli space, so it's, as long as you have an action up to gauge the trunk, you just lift it somehow.
Yeah, I mean, it's
Is that what's worrying you, Joe?
okay, well, so let me make this.
We could just pull the
phone
bundle back. You
Yeah,
don't
but
need
you don't need an isomorphism of the bundle as a pullback, you know, technically speaking, but I mean, it's fine, you know. Up to gauge, it's fine.
Our first theorem is kind of a gluing theorem to this effect. How do I want to state it? So let's say we let y1 up to yn be a configuration of distinct points, distinct non-zero points. In R3, and let me also choose M0, M1, MK. Sorry, And then in, right, okay, first I should fix a partition. Right, and so I'm partitioning my integer, which is the charge, into n plus 1 subcharges, and the k0 charge is going to be a little bit special. So this is going to be out of the moduli space, so this is just the regular charge k0 moduli space, and then the rest of them are going to be centered. So I choose monopole representatives, so one of charge k naught, which can be sort of any monopole, not necessarily centered at the origin, and then n monopoles of charges k1 up to kn, which are centered. The idea is this guy is going to be sort of left behind, and then these guys are going off to infinity in different directions. So then there exists a one parameter family, and epsilon of mk, such that what happens the way I'm stating it's going to be kind of the reverse of this. So rather than starting with a sequence of monopoles, I'm sort of taking this this cluster configuration and producing a family of monopoles that are going to limit to it. So such that as epsilon goes to 0, say this m of epsilon translated minus y over epsilon, again, translation converges mj, I guess, and converges in a weak sense, I suppose. Geometrically, it's going to be a little bit clearer what's going on when I write down this space on which this is all happening. So this is for j from n. And then for j0, so this is just m without translation. This is going to converge just to m0, the one that's left behind. So if we follow each of these, so all the yj are non-zero, and then if I divide by epsilon, that scales them out to infinity. So if I follow the monopole out to infinity, I see a cluster lower charge, and then if I stay behind, I see this cluster at charge 0. This slightly understates what we prove. So in fact, there's a bunch of parameters going on here. Like I've chosen the configurations of points, I've chosen the monopoles, and in fact, this construction is smooth with respect to these choices. So with respect to the choice of points and the monopoles, in fact, I get a smooth map from the data of configurations of points and these monopole moduli spaces into the monopole moduli space, and this is a local diffeomorphism on its image. So this is for sufficiently small epsilon. And I'll just say it in words. I won't be able to talk about it due to time, I think, but we're also able to, so there's a sense in which this thing has a complete asymptotic expansion down to epsilon equals 0. At the moment, it doesn't make sort of a lot of sense to see what that means, but we can pull back the L2 metric on the monopole moduli space to the parameter space, so this point configurations in monopole, the space of that data, and we get the asymptotics of the metric, which are explicitly computable to, I think, 2 terms in terms of that data. And they generalize the asymptotic metric of Gibbons and Manton, who gave the asymptotic metric in essentially this case where there's nothing left behind and the monopoles going out to infinity are all charge 1, so just widely separated single monopoles.
So you're saying that you know what the L2 metric is in terms of the L2 metrics on the pieces.
That's right. Yeah, that's right. In terms of the the metrics here are the L2 metrics. There's an obvious metric on configuration of points, so the Riemannian metric. That's right. And so we can write down in terms of that.
Are you going to say explicitly or implicitly anything about these phases? You mentioned these Y's explicitly, these sort of positions.
Right. Yeah, you'll see what happens with the phases.
There's a phase in the gluing.
Absolutely, yeah. You will see what's going to happen with that. So,
say something about that.
yeah. So that's the statement of the theorem for the purpose of this talk. And I think it will be, so hopefully it's going to make a little bit more sense if I actually give a sense of the construction of this, how this is accomplished. So in keeping with the theme that Pierre introduced this morning, which was to take an analysis problem, some kind of singular analysis problem, and then come up with a geometry that resolves it. So the singular analysis problem here is that, we want some sort of space which is going to capture the limits as epsilon goes to 0 of these monopole clusters going out to infinity. So, the usual way to prove a gluing theorem in geometry is you take some finite but small epsilon, produce an approximate solution, and then sort of fix it up. But really what I want to do is construct some space where I can really actually take the limit seriously at epsilon equals 0 and develop an asymptotic expansion. So here's the space on which we're going to construct just a single one-parameter family of monopoles. So that's the gluing space. So again, I've fixed my parameters. I've fixed this configuration of non-zero points, and I'm fixing monopoles in these lower charge moduli spaces. So, so let's consider these trajectories. I'll call them Zj, which is Yj divided by epsilon, right? So since Yj are non-zero, as epsilon goes to 0, these form straight lines in R3. Let me let x be the radial compactification of R3, and then I'll just denote by I the parameter interval in epsilon. I'll just take b0 to 1 for now. So now we're going to look at what happens inside the space. In x times I, what do these trajectories look like? So this is this, here's x, here's I, projecting down the interval. So I have my configuration at distinct points. It's on epsilon, and of course as epsilon goes to 0, they all go out to infinity. So here's the radial boundary of x down here, and this is epsilon equals 0 over here. So these just form straight lines that all go into the corner. Right, so the first thing I want to do is resolve the geometry of this space so that these trajectories have distinct limits. So step 1 is denoted by Z1. This is not quite the space I want yet, but it's an intermediate space. This product, and then I'm going to perform the real blow-up of the boundary of x across the boundary of I. So the boundary of x, which is just, of course, the two-sphere at infinity, times 0. So now this space looks like this. So again, this is, as Pierre said, just taking polar coordinates seriously at this corner. I replace this corner by an entire two-sphere times an interval's worth of points. This has the property that these trajectories now have distinct limits.
But given that the y's, oh right, because the y's could be collinear, so that's why you need to.
Yeah, that's right.
So that's why. Yeah, okay.
Yeah, so we're not quite done yet. That's right. So, so this new boundary face that I created when we blew up, let me call that D1. So it just looks. I mean, this is the inward pointing spherical normal bundle of S2, which is just an interval. So it's S2 times an interval. For various reasons, I want to think of this interval as being a closed interval from 0 to infinity, where 0 is up here and infinity is out here. And then I want to really think of this cylinder as being the radial compactification of R3, but blown up at the origin. So I have an R3, there's the radial infinity, and I blew up at the origin there. See why that is convenient to do in a second. But then the point is that the Z, J, epsilons have limits on D1. So this is almost the space on which I want. So the idea here, so so for each fixed epsilon, the fiber of this is of course just an R3. That's almost true here as well. So for epsilon positive, these fibers are still just radially compactified R3 again. But for epsilon equals 0, the preimage of epsilon equals 0 is the union of these two boundary hypersurfaces. The idea is I'm going to construct my family of monopoles, so there's going to be a monopole on each fiber depending on epsilon. and I want the geometry to capture this limit so that the monopole really is breaking up into widely separated monopole clusters at infinity. At the moment, there's not yet a place for those monopole clusters to live. So the second step is my actual gluing space. I'm going to take this intermediate space, V1, and I'm going to blow it up at the limits of all these trajectories. So I'll blow it up at Z1, 0, up to Zn, 0. So now the space looks like this. This is my gluing space Z. So it still has maps down to I, which I'll call pi I. And it has a map to X, called pi X. And the fibers for epsilon positive are, of course, just being impacted by R3, but the fiber over epsilon equals 0 is now a number of boundary faces, which I will denote by, so these new boundary faces that I constructed by blowing up, I'm going to call those x1 up to xn. The old boundary face, so the lift of the old boundary face at epsilon equals 0, I'm going to call that x0. So this is the space on which the monopole that is left behind is going to live. And then the lift of D1 I'm going to call D. So D is this space that interpolates between the x1 up to xn's and x0. And we'll call this remaining boundary hypersurface B, just give it a name. So what do these boundary faces look like topologically? Well, this is just a point of, these trajectories just have codimension 3, right? So when I blow them up, I'm just going to get radially compactified R3s again. So each of the xj's is diffeomorphic to radially compactified R3. And in fact, since I chose this configuration, I really get a legitimate origin. I mean, naturally it's just an affine space, but I really get an origin by taking the origin to be the limit of the lifted trajectory. So I really have an actual geometric identification of things with radially compactified three-dimensional real vector space. Now what does D look like? So this is J equals 0 up to n. And D looks like a radially compactified R3. Well, it used to look like that where I blew it up at the origin, and now I blew it up at a bunch of other points as well, so it's just like you take R3 and you blow up at Z0 up to Zn, where Z0 is the origin. From that point of view, I just blew up some more points. So the idea is that now this is the right kind of space to hold this limiting monopole configuration in infinity. So there's an entire Euclidean space in which each of my monopoles can live. And then there's this kind of interim space between them. And it looks like essentially another R3 with a bunch of points blown up. And these spaces meet, right? Like the radial boundary of the xj corresponds with the sort of conical boundary that I get by blowing up an interior point in R3. And you'll see that the natural sort of intermediate data that's going to interpolate between these monopoles is a Dirac monopole. So I'll try to motivate that.
Do these things have a metric structure?
Yeah, they will. So I'll talk about the metric in just a second. So in fact, right now. So that's what the space looks like topologically. So what's the metric, the geometry that we want to consider? So we're going to consider I'm going to pull back the Euclidean metric from R3. And that's going to give me some kind of metric on this space. And first let me sort of motivate what it looks like. So restricted to these, the question you want to ask is what does this metric behave like at these different boundary faces? So obviously it's not a metric in the usual sense on this space because it's only a metric in the sort of fiber-wise direction with respect to the projection to I. But on these fibers, on the interior fibers, of course it's just the usual metric on R3. What does it look like on these boundary fibers over epsilon equals 0? If you work it out, G restricts over the xj to be Euclidean metric again. With respect to this identification of the xj's with R3. So that's not so interesting. Well, I mean, it's interesting and nice. But slightly more subtle is what happens at D. So in fact, there's the metric is degenerate over D. Sorry, not degenerate, it's singular at D. It blows up like epsilon squared at D. But if I rescale it by epsilon squared and then restrict to D, what I get is, well, again, sort of the Euclidean metric, really the natural, the lift of the Euclidean metric to this space with the blowups. I mean, you just take R3 with the metric and blow up a bunch of points. I mean, now I just have I have a big conic end, the big end of the cone end, and I have little small ends of the cone ends. So it's asymptotically conic in both senses. So as a conic metric. That's the geometry. It's again very much Euclidean geometry, except that there's this interesting rescaling that happens at D. So in the theme introduced by Pierre, the best way to do this is to introduce the right bundle that captures this rescaling. So I'm going to define what I call the gluing tangent bundle, gamma TZ on this space. I can define it by the property that the space of all its smooth sections is a particular subalgebra of vector fields on Z. The gluing vector fields, which are going to be precisely the vector fields of the form, I should have said up here. Let me choose, so rho D, rho B, rho Xj are going to be boundary defining functions. I'm going to denote by rho X the product of all the boundary defining functions for all the X's. So if you think about what does epsilon look like as a function here, well, it's a function that vanishes at all the X's and the D's, and I can choose these boundary defining functions and choose them so that epsilon is the product of rho D and rho X. Okay, so what is this Lie subalgebra of vector fields? It's the vector fields which are rho D, rho B times a vector field which is tangent to the fibers of this projection to my parameter interval, as well as all the boundary faces. So that turns out to be the right geometric version of the tangent bundle in this space. It's sort of the vertical tangent bundle, but rescaled a little bit. So the significance is that there's a natural isomorphism between, there's a natural isomorphism between, so if you're doing Euclidean monopoles on X, just compactified R3, the right version of the tangent bundle is what's called the scattering tangent bundle. I won't define that, but it's the bundle which has sections consisting of bounded length with respect to the Euclidean metric. So that is, it's the right bundle there. There's a natural isomorphism between the pullback of that thing to this gluing space and this gluing bundle. And then there are restrictions of this gluing bundle to these boundary faces. TZ restricted to Xj, just like the scattering tangent bundle, that particular Euclidean face. And then there's a rescaling that happens at D. So there's a map with multiplication by epsilon inverse that identifies this isomorphically with the scattering / conic tangent bundle of D. So just as a conic space. Okay. So that's for the geometry. Now we want to consider the Bogomolny equation on this space. I'll leave a picture. So I'm gonna, let's say, lift and lift E from X to Z, so I can just pull back my standard SU2 bundle from Z. guess I'll call it E. Okay, great. And now we're going to consider what the Bogomolny equation looks like for on this gluing space. So let's consider, just for motivational purposes, a connection and a Higgs field. So it's going to be a connection on E and a smooth section of the adjoint bundle associated to E. Just smooth for the moment. I'm going to have to weaken the smoothness in a second. And then let's consider the Bogomolny equation. So let me define Bogomolny operator to be star. I'll put the star over here, minus dA phi. This star is star associated to this metric. Right? So it's just this fiber-wise sort of gamma metric. So of course, if I have a connection and Higgs field for which this is 0 on my whole space, then I have a fiber-wise family of solutions to the monopole equations. The scaling does some interesting things. So, right, so what I want to say. So the right way to interpret this, again, in this theme of using the correct tangent bundles, is I want to consider these as gamma 1 forms. E, so we're gamma k, z is these sections of the dual bundle, exterior power of the dual gamma t star z. Now there is in fact a natural map from the ordinary cotangent bundle of z to the gamma cotangent bundle of z. So first of all, if I have ordinary cotangent bundle, I can restrict it to the fibers, and then undo this scaling, I get it. So this induces a map from ordinary forms of degree k on z because of the rho d rho b. If you sort of lift an ordinary form to a gamma form, it's going to vanish to order k, the degree of the form, at d and d as a gamma form. So at the moment, this is just an honest connection and a SU2 valued function essentially. So its covariant derivative is the usual thing, just has an ordinary 1 form. But in order to utilize the geometry, I want to consider this as a gamma form. If I do that, then the Hodge star is an isomorphism between these bundles. So there's no scaling. So if I rescale the bundle, then there's no scaling going on in the Hodge star. So because of this, just naturally, dA phi is ordered rho d, rho b, and f, since it's a 2 form, is ordered rho d squared, rho b squared, and then likewise star f is because star is just a global isomorphism on the exterior power bundles. Okay, so what do we want to do? We ultimately want to find a solution to this equation for small epsilon. As a first step, we're going to solve it formally in epsilon. So we want a solution that vanishes to order sort of epsilon to the infinity. So vanishes of all these boundary faces to infinite order.
So do I understand correctly? For non-zero epsilon, the fiber is the same as the rescale.
Yes. No, the fiber didn't get rescaled. Yeah, there's no rescaling going on in the fiber.
Is there any adjustment of the boundary conditions for the Higgs field?
You'll see what's going on in that. Yeah, I need to get to that. Just a second. Right. So one quick thing to get out of the way. Let's just note. So if a phi restricted to xj, right, the geometry there just looks like ordinary Euclidean space. Connection induces a connection in ordinary sense. If this satisfies, let's call that restriction aj phi j. If that vanishes on the boundary face, so solves the Bogomolny equations of that boundary face, then let's say for each j, then this configuration is going to be vanishing. Right, okay, so I've got a star FA. So this is order rho d squared rho b. That second term is order rho d rho b. So this is the sort of least order that's going on. So I get a just by virtue of solving the Von-Neumann equations on these faces, I get a solution to order rho d, let's see, rho x, rho d, rho b. Right. So now the more interesting things happen at d. So just because there's a mismatch at d, well, and also at b, between the order of vanishing of dA phi and the order of vanishing of the form, it follows that if dA phi equals 0, is viewed as an ordinary form over d and b, let's say, as an ordinary form, ordinary one form, then this thing is actually going to be viewed as a gamma form, going to be order rho d squared, rho b squared, so these orders match up. So then this is going to vanish over x if we solve the Von-Neumann equation over x, and then rho d squared, rho b squared. So I can improve the order just by having this sort of covariant constancy of the Higgs field over d and b. Now this implies that we have a reduction to U1. If we have a non-vanishing covariant constant section of the adjoint bundle, then I can immediately reduce all of my data to U1. That means that my SU, this E is actually associated to a circle bundle L. I mean, it looks like L, plus tensor L inverse of Michael introduced, and the connection reduces to a U1 connection. So everything sort of diagonalizes and abelianizes over D and B. So over B, this is my original infinity for my fibers. So I'm going to end up having a framing along B, consistent with the reduction of this structure group. And the structure group is reduced to U1 over D as well. So that's the sort of first order thing that happens at D. If I want to vanish to an additional order over this face D, let me point out what happens. So let me organize. Let's Taylor expand. I'm going to Taylor expand the Higgs field at D. So I'm going to write it as phi naught. So just to first order, so now I'm going to pull a little trick, and instead of calling this rho d phi 1, where phi 1 is a smooth function on D, I'm going to use the fact that epsilon is the product of rho d and rho b. I'm going to call this epsilon phi 1, where phi 1 is singular at all of the boundary faces where it meets x, which is going to be rho x inverse, smooth function on D. So if you do that, then the Von-Neumann equation expanded out near T looks like a dA phi naught, which we're assuming vanishes, plus so minus dA phi 1 plus the order increases by 1, and D is going to be rho d cubed. So this term is order rho d. This term is order rho d squared, and then I have remainder order rho d cubed. So we're already assuming that this vanishes, so I have a reduction of the structure group there. So what happens at this next level? Well, by rescaling, so this is written in terms of my gamma forms at the moment. I'd like to interpret this in terms of the geometry at D. In terms of the geometry at D, in terms of this rescaling, right, so let me just write it. So in terms of the rescaling at D, this looks like, so this first term is vanishing, so assume that's vanishing. I get the Hodge star of the induced metric on D now. I guess there's an squared out front here, but it doesn't really matter. I mean, the point is I can interpret this thing in terms of, so this is where dA denotes the honest connection. I mean, I started out with an honest connection, so it induces an honest connection on D. So in terms of that connection, this next order term, it's like this. And so for this to vanish, A over D, A is already a connection on my reduced bundle, so it's already an abelian connection. So in order for this equation to hold, phi 1 and this induced connection must be a Dirac monopole. Right, okay, so that's the situation. So that sort of motivates that initial data for our construction. So what we're going to have is frame-centered monopoles on these Euclidean faces. And a Dirac monopole, well, so a reduction of the gauge group to U1 over infinity and over this face D. And then we're going to put a Dirac monopole on that U1 bundle over D. And the restriction of the Dirac connection to these little spheres where you blew up is going to give us a framing for these Euclidean monopoles. So that's kind of the picture. So everything is consistent then with vanishing the equation. So,
Sorry, but the singularity is not living on D, though, or the Dirac monopole.
Because of the geometry, it's a little bit weird how it links up. The term in the Higgs field that's blowing up as you go in here gets linked up with the term that's vanishing to first order as you go to the boundary in X, just because of the way that things are written.
Right, so in some sense, D is carrying no charge.
D is going to, well, so the idea is that you're going to have charge, Ki monopoles here. The Dirac monopole has a degree around each of its singular points. So that's going to be exactly that degree, and then it's going to add up to the total degree out here, the total charge. Right.
What about the norm of the Higgs field?
What about the what?
The norm of the Higgs field.
The norm of the Higgs field. I'm going to take that to be 1 everywhere. So, I mean, you could prescribe it however you like. You could prescribe the mass, but I'm going to prescribe the mass just to be 1 out here. The leading order that the Higgs field at D, right, is just a covariant constant section. So really, in terms of the U1 reduction, this is just a constant function of 1, if I like. And then the next order term is my Dirac monopole.
You don't understand that to be a sum of contributions from each xi cluster.
Yeah. Yeah. The mass is not additive here. That's right. Okay. So am I essentially out of time? Should I state? So let me just maybe say in words what we want to do. So that motivates the initial data for our gluing construction. Exactly what I said. Centered monopoles here, and not necessarily centered monopole here, a Dirac monopole that interpolates between them. If I have all that data, then I'm going to solve, that initial data solves the equation to some order, I think it's like epsilon rho d squared, and it could be rho b squared as well. And then I just want to add formal terms to this to solve this iteratively to order epsilon to the infinity. So that involves studying the linear model operators of these boundary faces. So again, going along with the theme that Pierre introduced this morning, we have this geometry, and somehow these limiting boundary faces capture some kind of model operators whose behavior we want to know. So there's a lot of analysis that goes into the model operators. So it's essentially the linearized Bogomolny operator over the X and the linearized Dirac operator over D. And we want to know explicit solvability conditions. So essentially, if I denote by Lx and Ld, these linearized things, I want to know explicit solvability results of the form Lu equals F, where F has some polyhomogeneous expansion, so some expansion in terms of logs and powers and boundary defining functions, in terms of existence of a U in some other, and I want to know how the terms arising in the asymptotic expansion of U correspond with those in the asymptotic expansion of F. And so there's analysis that goes into doing that, and then once we have that information, we can take all the error terms and iteratively correct them alternately over the X faces and over the D face, one at a time. There's a quadratic term, but it's zeroth order and not too difficult. So by some iterative construction, we solve this formally to order epsilon to the infinity. And that tells us what all the asymptotics are going to be in the true solution. Then we have some rapidly vanishing error. Then there's a pseudo-differential parametrics construction and inverse function theorem that we use to remove that final error and get actually a true solution for sufficiently small epsilon. And then finally, so I omitted all the parameters, the monopoles, and the point configurations. Really, we can do this fiber-wise over that big parameter space. So this is really just one fiber of the overall blooming space. And the construction is manifestly smooth with respect to those parameters, so we get a smooth map in the moduli space. And we can explicitly differentiate it with respect to the parameters and look at the linearization of this map, see that it's an immersion of the right between smooth manifolds of the right dimension, so a local diffeomorphism. And that's also how we can analyze the metric by getting essentially pulling back tangent vectors to the moduli space. And then the metric pairing is just the L2 pairing, so I just take two linear solutions on this space obtained by differentiating in some of my parameters. I pair them and I integrate over the fibers. I get something with explicit expansions down here. Well, not explicit. I get something with a complete asymptotic expansion down here, and the first couple of terms are explicitly computable. So I'll stop there.
Questions?
These things have non-transforms, and the rank, I mean the charge, K, becomes the rank. And there's a natural gluing there, which is just diagonal embedding, where it mucks up the boundary conditions that you asked for the solution to Nahm's equation. But have you looked at how this picture sort of would non-transform, or
Yeah,
do you have an idea?
I don't. Michael has had a little bit more experience with the non-transform, so you might have.
I've thought about it, but I haven't done it.
Okay.
I mean, it should be doable.
Yeah, no, I mean,
It should be doable.
I mean, there's also just a question, like, can you see a reasonable compactification of the moduli space, for instance, in the rational maps picture? It's not as clear. I mean, we sort of see how to do this compactification in this direct analysis on the moduli space tack, and we can sort of see how the rest of the corners are going to go. Just a lot of work to write it down, but it's a good question. Can you see this same picture in the non-picture? I don't know.
And I think the picture you suggest, I don't know how clear the picture is. I mean, the picture you suggest, I'm sure it's right.
Yeah, I mean, there's work, right? Because
Yeah, right. I mean,
diagonal
yes, you've got the,
solutions,
yeah, sure.
but they sort of
It's kind of clear what you should try to do.
the polar structures, they're convenient.
Yes.
Did you answer Nick Manton's question about the phases?
Well, I guess, so the idea is that the framing, okay. So there is an overall phase. Of course, I could act by an overall phase on the whole data. But because I'm sort of picking a framing at this overall end, I'm fixing the overall phase. Because of the way that the Dirac moduli work, as Michael was explaining, if you frame the Dirac monopole at infinity, then there is a unique Dirac monopole up to gauge. So there is gauge freedom in the Dirac monopole down here at these orders, but the way that the Dirac monopole links up with the Euclidean monopole is at a lower order, as I said, right? So I mean, it's a little bit hard to see here. This phi naught corresponds to the leading term of the Higgs field in X at infinity. So that's fixed. That's just fixed to be a constant. There is gauge freedom that can act by U1 gauge transformations on the next order term. But the idea is that the sort of boundary values of this Dirac monopole at these little spheres give us maybe a non-standard framing, but a framing for the monopole moduli spaces. And so we take a representative for the moduli space with that given framing and glue that in.
I mean, a slightly different answer is, I mean, if you want to change the framing of the monopole in the face of the face x1, I mean, just infinitesimally, you can write down that's gauge transforming by the Higgs field of that monopole infinitesimally. So you can write down an approximate tangent vector. We didn't get to tangent vector. You write down an approximate tangent vector which is equal to that over x1 and extend it in some more or less obvious way over the rest of the boundary here. And you can figure out, I mean, you can explicitly compute the metric on that. And you can then wind the handle to say that you have a true tangent vector, which is approximately this as the boundary, and then you can compute the length squared of that tangent vector by these kinds of techniques. And I mean, it's what you'd expect. I mean, it's a leading order. We didn't get to that, but I mean, the metric decomposition is what you'd expect, in that it is Euclidean metrics on each of the Euclidean. I mean, you can move the Euclidean, you can move the configuration points, and you get a Euclidean metric multiplied though by the magnetic charge of the monopole there, and the phase is the same. So I mean, it's an R4 just scaled up by a factor of K1. K1 is the charge, and then the internal motion in the moduli space. I mean, so leading all of that, so you have a Euclidean product between a bunch of a Riemannian product, the leading order, between a bunch of Euclidean metrics and the metrics on the centered moduli space, the framed moduli spaces, centered moduli space. So I mean, it's what you'd guess, and it's consistent with Gibbon's mapping, of course. But I mean, it's kind of cool that you do get, if you have something of charge K1, then the metric is, it's that much heavier by a factor of K1, which is, I suppose, what you'd expect. Does that?
Yes.
Yeah. Okay.
So, you described head compactification of moduli space of monopole. How is this compactification better than other compactifications? For
Well,
example, does it capture K2 homology as
Funny you should ask.
well, I mean, yeah, I mean, that's right. The idea is to magnetize it in such a way that we can work out the asymptotic behavior of the metric. And then, I mean, so still to come is what happens at the corners, which I think goes into understanding, what the L2 cohomology ends up being. I mean, so at this level, we still can't work out what the L2 cohomology is precisely, because you need to know what happens at all the corners.
But there's just a statement that you don't know what happens when the J's are the same. I mean, they could be the same.
No, it's not exactly that. It's more that the clusters are going out, but at incomparable rates. So I have, let's say, like a sort of 3 clusters going out, but 2 of them are going out much faster than the third. Right? So there's sort of a sense in which these split off, but then at a lower order at infinity, these are kind of splitting off at infinity. That relates to actually, the boundary, the iterative compactification of the lower charge.
Right, but I mean,
No, I think you're right, Anne. I mean, there's one of these faces for every partition of K in these things.
Yeah.
And then how those spaces
How
meet.
they fit together.
How they meet
Well,
together.
it's kind of clear how they meet, but
Yeah.
what's happening metrically is
Right,
less
yeah,
clear.
yeah.
But I mean, so that's exactly it.
Why do you say it's clear how they meet? So, I mean, this has described a codimension 1 face.
Yeah.
So what's the picture of a codimension 2 face?
Well, it's a little ugly, so I won't try to draw it. But I mean, I would say that we understand it. I mean, so the parameters minus epsilon essentially give you the boundary hypersurface. So it's essentially, it's not actually a product of the monopole moduli spaces and the point configurations. It's a bundle of monopole moduli spaces over the point configurations. There is some topology there.
That's just within the codimension 1 face.
Within the
Yes,
codimension
okay,
1 phase.
Right.
So then, so inductively, we will have compactified those lower charge moduli spaces. So those boundary hypersurfaces are going to have, boundaries themselves. And we have there's sort of a simpler model. There's a nice resolution of the configuration of just points, let's say in compactified R3, that serves as kind of a model for how these things are going to fit together. So I'd say I think we understand it, but it's, it's combinatorially
Depends what you
complicated.
mean by understand.
I mean, just like over here, you essentially have epsilon and the boundary face, and you have product
Yeah, there's going to be
structure.
2 epsilons.
You need,
Yeah,
you need
exactly,
that
yeah.
chart. You need a chart with
Yeah,
2
absolutely.
That's right.
epsilons.
Yeah, and I can draw horrible pictures that look like tubes splitting into other tubes and things, and that's kind of what the gluing space for that is.
Should these different codimension 1 pieces be conventional metrically? Because you expect generically that it's splits into individual particles.
Mhm.
And then sort of in codimension one or higher codimension, where they're sort of, the clumps get bigger and bigger, but that somehow represents, at least in the rational map space, the smaller strata. So here it's a little bit more than, okay, fine, it's codimension one, but it's somehow smaller than you know, the partition 1, 1, 1, 1, 1 should be somehow bigger.
I guess, yeah, I don't quite understand in what sense bigger or smaller.
Well, just the generic rational map has, you know, poles, basically. Sort of picture.
Yeah, I mean, I guess I would just say that, I mean, there's sort of there's going to be a nice consistent picture of all the metric asymptotics so that they fit together, and it's going to be a complete asymptotic expansion on a manifold with corners. I mean, I think that, like, yeah, I think we can just sort of sit down and try to, like, guess what the expansion is going to look like, at least in codimension 2, without even doing the Boolean construction. We haven't done that yet, but.
But in terms of parameter count, they all have the same size. I mean, 1, 1, 1, 1 is no different from any other.
Yeah, well, that's the sort of odd, and yet.
Well, I
But
mean,
when you blow
the-
stuff up, then genericity changes.
Yeah, yeah.
I mean, that's sort of,
And the dimension of the moduli space is larger though. I mean, you have fewer configurations, but you have more moduli parameters. So that's what this is reflecting.
okay.